Soil is the mixture of minerals, organic matter, gases, liquids and a myriad of organisms that can support plant life. It is a natural body that exists as part of the pedosphere and it performs four important functions. It is a medium for plant growth. It is a means of water storage, supply and purification. It is a modifier of the atmosphere. And it is a habitat for organisms that take part in decomposition and creation of a habitat for other organisms. Soil is considered the skin of the Earth with interfaces between the lithosphere, hydrosphere, atmosphere, and biosphere. Soil consists of a solid phase as well as a porous phase that holds gases and water. Accordingly, soils are often treated as a three-state system. Soil is the end product of the influence of the climate, relief, biotic activities, and parent materials interacting over time. Soil continually undergoes development by way of numerous physical, chemical and biological processes, which include weathering with associated erosion. Most soils have a density between 1 and 2 gram per centimeter 3. Little of the soil of planet Earth is older than the Pleistocene and none is older than the Cenozoic, although fossilized soils are preserved from as far back as the Archean. Soil science has two main branches of study, edaphology and pedology. Pedology is focused on the formation, description, and classification of soils in their natural environment, whereas edaphology is concerned with the influence of soils on organisms. In engineering terms, soil is referred to as regolith, or loose rock material that lies above the solid geology. Soil is commonly referred to as earth, or dirt. Technically, the term dirt should be restricted to displaced soil. As soil resources serve as a basis for food security, the international community advocates for its sustainable and responsible use through different types of soil governance. Overview. Soil is a major component of the Earth's ecosystem. From ozone depletion and global warming to rainforest destruction and water pollution, the world's ecosystems are impacted in far-reaching ways by the processes carried out in the soil. Soil is the largest superficial global carbon reservoir on Earth, and it is potentially one of the most reactive to human disturbance and climate change. As the planet warms, soils will add carbon dioxide to the atmosphere due to its increased biological activity at higher temperatures. Thus, soil carbon losses likely have a large positive feedback response to global warming. Soil acts as an engineering medium, a habitat for soil organisms, a recycling system for nutrients and organic wastes, a regulator of water quality, a modifier of atmospheric composition, and a medium for plant growth. Since soil has a tremendous range of available niches and habitats, it contains most of the Earth's genetic diversity. A handful of soil can contain billions of organisms, belonging to thousands of species. Soil has a mean prokaryotic density of roughly 10-13 organisms per cubic meter, whereas the ocean has a mean prokaryotic density of roughly 108 organisms per cubic meter. The carbon content stored in soil is eventually returned to the atmosphere through the process of respiration, which is carried out by heterotrophic organisms that feed upon the carbonaceous material in the soil. Since plant roots need oxygen, ventilation is an important characteristic of soil. This ventilation can be accomplished via networks of soil pores, which also absorb and hold rainwater, making it readily available for plant uptake. Since plants require a nearly continuous supply of water, but most regions receive sporadic rainfall, the water-holding capacity of soils is vital for plant survival. Soils can effectively remove impurities, kill disease agents, and degrade contaminants. Typically, soils maintain a net absorption of oxygen and methane, and undergo a net release of carbon dioxide and nitrous oxide. Soils offer plants physical support, air, water, temperature moderation, nutrients, and protection from toxins. Soils provide readily available nutrients to plants and animals by converting dead organic matter into various nutrient forms. Soils supply plants with mineral nutrients held in place by the clay and humus content of the soil. For optimum plant growth, the generalized content of soil components by volume should be roughly 50% solids, and 50% voids, of which half is occupied by water and half by gas. The percent soil mineral and organic content is typically treated as a constant, while the percent soil water and gas content is considered highly variable, whereby a rise in one is simultaneously balanced by a reduction in the other. The pore space allows for the infiltration and movement of air and water, both of which are critical for life in soil. Compaction, a common problem with soils, reduces this space, preventing air and water from reaching the plant roots and soil organisms. Given sufficient time, an undifferentiated soil will evolve a soil profile which consists of two or more layers, referred to as soil horizons, that differ in one or more properties such as in their texture, structure, density, porosity, consistency, temperature, color, and reactivity. The horizons differ greatly in thickness and generally lack sharp boundaries. Soil profile development is dependent on the processes that form soils from their parent materials, the type of parent material, and the factors that control soil formation. The biological influences on soil properties are strongest near the surface, while the geochemical influences on soil properties increase with depth. Mature soil profiles in temperate climate regions typically include three basic master horizons, A, B and C. The soil normally includes the A and B horizons. The living component of the soil is largely confined to the soil. In the more hot, humid, climate of the tropics, a soil may have a single horizon. The soil texture is determined by the relative proportions of sand, silt, and clay in the soil. The addition of organic matter, water, gases and time causes the soil of a certain texture to develop into a larger soil structure called an aggregate. At that point a soil can be said to be developed, and can be described further in terms of color, porosity, consistency, reaction etc. Of all the factors influencing the evolution of soil, water is the most powerful due to its involvement in the solution, erosion, transportation, and deposition of the materials of which a soil is composed. The mixture of water and dissolved and suspended materials is called the soil solution. Since soil water is never pure water, but contains hundreds of dissolved organic and inorganic substances, it may be more accurately called the soil solution. Water is central to the solution, precipitation and leaching of minerals from the soil profile. Finally, water affects the type of vegetation that grows in a soil, which in turn affects the development of the soil profile. The most influential factor in stabilizing soil fertility are the soil colloidal particles, clay and humus, which behave as repositories of nutrients and moisture and so act to buffer the variations of soil solution ions and moisture. The contribution of soil colloids to soil nutrition are out of proportion to their part of the soil. Colloids act to store nutrients that might otherwise be leached from the soil or to release those ions in response to changes of soil pH, and so, to make them available to plants. The greatest influence on plant nutrient availability is soil pH, which is a measure of the hydrogen ion soil reactivity, and is in turn a function of the soil materials, precipitation level, and plant root behavior. Soil pH strongly affects the availability of nutrients. Most nutrients, with the exception of nitrogen, originate from minerals. Some nitrogen originates from rain, but most of the nitrogen available in soils is the result of nitrogen fixation by bacteria. The action of microbes on organic matter and minerals may be to free nutrients for use, sequester them, or cause their loss from the soil by their volatilization to gases or their leaching from the soil. The nutrients may be stored on soil colloids, and live or dead organic matter, but they may not be accessible to plants due to extremes of pH. The organic material of the soil has a powerful effect on its development, fertility, and available moisture. Following water and soil colloids, organic material is next in importance to soil's formation and fertility. History of the study of soil, studies concerning soil fertility. The history of the study of soil is intimately tied to our urgent need to provide food for ourselves and forage for our animals. Throughout history, civilizations have prospered or declined as a function of the availability and productivity of their soils. The Greek historian Xenophon is credited with being the first to expound upon the merits of green manuring crops, but then whatever weeds are upon the ground, being turned into earth, enrich the soil as much as dung. Columella unregistered trademark S. Husbandry, circa 60 AD, advocated the use of lime and that clover and alfalfa should be turned under, and was used by 15 generations under the Roman Empire until its collapse. From the fall of Rome to the French Revolution, knowledge of soil and agriculture was passed on from parent to child, and as a result, crop yields were low. During the European Dark Ages, Yahya ibn al-Awwam unregistered trademark S. Handbook, with its emphasis on irrigation, guided the people of North Africa, Spain and the Middle East. A translation of this work was finally carried to the southwest of the United States. Experiments into what made plants grow first led to the idea that the ash left behind when plant matter was burned was the essential element, but overlooked the role of nitrogen, which is not left on the ground after combustion. In about 1635, the Flemish chemist Jan Baptist van Helmont thought he has proved water to be the essential element from his famous 5 years experiment with a willow tree grown with only the addition of rainwater. His conclusion came from the fact that the increase in the plant's weight had apparently been produced only by the addition of water, with no reduction in the soil's weight. John Woodward experimented with various types of water ranging from clean to muddy and found muddy water the best, and so he concluded that earthy matter was the essential element. Others concluded it was humus in the soil that passed some essence to the growing plant. Still others held that the vital growth principle was something passed from dead plants or animals to the new plants. At the start of the 18th century, Jethro Tull demonstrated that it was beneficial to cultivate the soil, but his opinion that the stirring made the fine parts of soil available for plant absorption was erroneous. As chemistry developed, it was applied to the investigation of soil fertility. The French chemist Antoine Lavoisier showed in about 1778 that plants and animals must combust oxygen internally to live, and was able to deduce that most of the 165-pound weight of Van Helmont unregistered trademark S. willow tree derived from air. It was the French agriculturalist Jean-Baptiste Boussingault who by means of experimentation obtained evidence showing that the main sources of carbon, hydrogen and oxygen for plants were the air and water. Justus von Liebig in his book Organic Chemistry and its Applications to Agriculture and Physiology, asserted that the chemicals in plants must have come from the soil and air, and that to maintain soil fertility, the used minerals must be replaced. Liebig nevertheless believed the nitrogen was supplied from the air. The enrichment of soil with guano by the Incas was rediscovered in 1802, by Alexander von Humboldt. This led to its mining and that of Chilean nitrate, and to its application to soil in the United States and Europe after 1840. The work of Liebig was a revolution for agriculture, and so other investigators started experimentation based on it. In England, John Bennett Laws and Joseph Henry Gilbert worked in the Rothamsted Experimental Station, founded by the former, and discovered that plants took nitrogen from the soil, and that salts needed to be in an available state to be absorbed by plants. Their investigations also produced the superphosphate, consisting in the acid treatment of phosphate rock. This led to the invention and use of salts of potassium and nitrogen as fertilizers. Ammonia generated by the production of coke was recovered and used as fertilizer. Finally, the chemical basis of nutrients delivered to the soil and manure was understood, and in the mid-19th century chemical fertilizers were applied. However, the dynamic interaction of soil and its life forms awaited discovery. In 1856 J.T. Way discovered that ammonia contained in fertilizers was transformed into nitrates, and 20 years later R. W. Warrington proved that this transformation was done by living organisms. In 1890 Sergei Winogradsky announced he had found the bacteria responsible for this transformation. It was known that certain legumes could take up nitrogen from the air and fix it to the soil, but it took the development of bacteriology towards the end of the 19th century to lead to an understanding of the role played in nitrogen fixation by bacteria. The symbiosis of bacteria and leguminous roots, and the fixation of nitrogen by the bacteria, were simultaneously discovered by German agronomist Hermann Hegel and Dutch microbiologist Martinus Bijgerink. Crop rotation, mechanization, chemical and natural fertilizers led to a doubling of wheat yields in Western Europe between 1800 and 1900. Studies concerning soil formation. The scientists who studied the soil in connection with agricultural practices had considered it mainly as a static substrate. However, soil is the result of evolution from more ancient geological materials. After studies of the improvement of the soil commenced, others began to study soil genesis and as a result also soil types and classifications. In 1860, in Mississippi, Eugene W. Hilgard studied the relationship among rock material, climate, and vegetation, and the type of soils that were developed. He realized that the soils were dynamic, and considered soil types classification. Unfortunately, his work was not continued. At the same time, Vasily Dokuchev was leading a team of soil scientists in Russia who conducted an extensive survey of soils, finding that similar basic rocks, climate and vegetation types lead to similar soil layering and types, and established the concepts for soil classifications. Due to the language barriers, the work of this team was not communicated to Western Europe until 1914 by a publication in German by K.D. Glinka, a member of the Russian team. Curtis F. Marbut was influenced by the work of the Russian team, translated Glinka's publication into English, and as he was placed in charge of the U.S. National Cooperative Soil Survey, applied it to a national soil classification system. Soil forming processes. Soil formation, or pedogenesis, is the combined effect of physical, chemical, biological and anthropogenic processes working on soil parent material. Soil is said to be formed when organic matter has accumulated and colloids are washed downward, leaving deposits of clay, humus, iron oxide, carbonate, and gypsum. These constituents are moved from one level to another by water and animal activity. As a result, layers form in the soil profile. The alteration and movement of materials within a soil causes the formation of distinctive soil horizons. How soil formation proceeds is influenced by at least 5 classic factors that are intertwined in the evolution of a soil. They are, parent material, climate, topography, organisms, and time. When reordered to climate, relief, organisms, parent material, and time, they form the acronym CROPT. An example of the development of a soil would begin with the weathering of lava flow bedrock, which would produce the purely mineral-based parent material from which the soil texture forms. Soil development would proceed most rapidly from bare rock of recent flows in a warm climate, under heavy and frequent rainfall. Under such conditions, plants become established very quickly on basaltic lava, even though there is very little organic material. The plants are supported by the porous rock as it is filled with nutrient-bearing water that carries dissolved minerals from the rocks and guano. Crevasses and pockets, local topography of the rocks, would hold fine materials and harbor plant roots. The developing plant roots are associated with mycorrhizal fungi that assist in breaking up the porous lava, and by these means organic matter and a finer mineral soil accumulate with time. Parent material. The mineral material from which a soil forms is called parent material. Rock, whether its origin is igneous, sedimentary, or metamorphic, is the source of all soil mineral materials and the origin of all plant nutrients with the exceptions of nitrogen, hydrogen and carbon. As the parent material is chemically and physically weathered, transported, deposited and precipitated, it is transformed into a soil. Typical soil mineral materials are quartz CO2, calcite, Ca-CO3, feldspar, Cal C308, mica, K, Mg, Fe, 3Al C3O10, OH, 2. Classification of parent material. Parent materials are classified according to how they came to be deposited. Residual materials are mineral materials that have weathered in place from primary bedrock. Transported materials are those that have been deposited by water, wind, ice or gravity. Cumulose material is organic matter that has grown and accumulates in place. Residual soils are soils that develop from their underlying parent rocks and have the same general chemistry as those rocks. The soils found on mesas, plateau, and plains are residual soils. In the United States as little as 3% of the soils are residual. Most soils derive from transported materials that have been moved many miles by wind, water, Ice and gravity. Aeolian processes are capable of moving silt and fine sand many hundreds of miles, forming loess soils, common in the Midwest of North America and in Central Asia. Clay is seldom moved by wind as it forms stable aggregates. Water-transported materials are classed as either alluvial, lacustrine, or marine. Alluvial materials are those moved and deposited by flowing water. Sedimentary deposits settled in lakes are called lacustrine. Lake Bonneville and many soils around the Great Lakes of the United States are examples. Marine deposits, such as soils along the Atlantic and Gulf coasts and in the Imperial Valley of California of the United States, are the beds of ancient seas that have been revealed as the land uplifted. Ice moves parent material and makes deposits in the form of terminal and lateral moraines in the case of stationary glaciers. Retreating glaciers leave smoother ground moraines and in all cases, outwash plains are left as alluvial deposits are moved downstream from the glacier. Parent material moved by gravity is obvious at the base of steep slopes as talus cones and is called colluvial material. Cumulose parent material is not moved but originates from deposited organic material. This includes peat and muck soils and results from preservation of plant residues by the low oxygen content of a high water table. While peat may form sterile soils, muck soils may be very fertile. Weathering of parent material. The weathering of parent material takes the form of physical weathering, chemical weathering and chemical transformation. Generally, minerals that are formed under the high temperatures and pressures at great depths within the Earth's mantle are less resistant to weathering, while minerals formed at low temperature and pressure environment of the surface are more resistant to weathering. Weathering is usually confined to the top few meters of geologic material, because physical, chemical, and biological stresses generally decrease with depth. Physical disintegration begins as rocks that have solidified deep in the earth are exposed to lower pressure near the surface and swell and become unstable. Chemical decomposition is a function of mineral solubility, the rate of which doubles with each 10°C rise in temperature, but is strongly dependent on water to affect chemical changes. Rocks that will decompose in a few years in tropical climates will remain unaltered for millennia in deserts. Structural changes are the result of hydration, oxidation, and reduction. Physical disintegration is the first stage in the transformation of parent material into soil. Temperature fluctuations cause expansion and contraction of the rock, splitting it along lines of weakness. Water may then enter the cracks and freeze and cause the physical splitting of material along a path toward the center of the rock, while temperature gradients within the rock can cause exfoliation of shells. Cycles of wetting and drying cause soil particles to be abraded to a finer size, as does the physical rubbing of material as it is moved by wind, water, and gravity. Water can deposit within rocks minerals that expand upon drying, thereby stressing the rock. Finally, organisms reduce parent material in size through the action of plant roots or digging on the part of animals. Chemical decomposition and structural changes result when minerals are made soluble by water or are changed in structure. The first three of the following list are solubility changes and the last three are structural changes. The solution of salts in water results from the action of bipolar water on ionic salt compounds producing a solution of ions and water. Hydrolysis is the transformation of minerals into polar molecules by the splitting of the intervening water. This results in soluble acid-base pairs. For example, the hydrolysis of orthoclase feldspar transforms it to acid silicate clay and basic potassium hydroxide, both of which are more soluble. In carbonation, the reaction of carbon dioxide in solution with water forms carbonic acid. Carbonic acid will transform calcite into more soluble calcium bicarbonate. Hydration is the inclusion of water in a mineral structure, causing it to swell and leaving it more stressed and easily decomposed. Oxidation of a mineral compound is the inclusion of oxygen in a mineral, causing it to increase its oxidation number and swell due to the relatively large size of oxygen, leaving it stressed and more easily attacked by water or carbonic acid. Reduction, the opposite of oxidation, means the removal of oxygen, hence oxidation number of some part of the mineral is reduced, which occurs when oxygen is scarce. The reduction of minerals leaves them electrically unstable, more soluble and internally stressed and easily decomposed. Of the above, hydrolysis and carbonation are the most effective. Saprolite is a particular example of a residual soil formed from the transformation of granite, metamorphic and other types of bedrock into clay minerals. Often called weathered granite, saprolite is the result of weathering processes that include hydrolysis, chelation from organic compounds, hydration and physical processes that include freezing and thawing. The mineralogical and chemical composition of the primary bedrock material, its physical features, including grain size and degree of consolidation, and the rate and type of weathering transform the parent material into a different mineral. The texture, pH and mineral constituents of saprolite are inherited from its parent material. Climate. The principal climatic variables influencing soil formation are effective precipitation and temperature, both of which affect the rates of chemical, physical, and biological processes. The temperature and moisture both influence the organic matter content of soil through their effects on the balance between plant growth and microbial decomposition. Climate is the dominant factor in soil formation, and soils show the distinctive characteristics of the climate zones in which they form. For every 10 degrees Celsius rise in temperature, the rates of biochemical reactions more than double. Mineral precipitation and temperature are the primary climatic influences on soil formation. If warm temperatures and abundant water are present in the profile at the same time, the processes of weathering, leaching, and plant growth will be maximized. Humid climates favor the growth of trees. In contrast, grasses are the dominant native vegetation in subhumid and semi-arid regions, while shrubs and brush of various kinds dominate in arid areas. Effective precipitation. Water is essential for all the major chemical weathering reactions. To be effective in soil formation, water must penetrate the regolith. The seasonal rainfall distribution, evaporative demand, site topography, and soil permeability interact to determine how effectively precipitation can influence soil formation. The greater the depth of water penetration, the greater the depth of weathering of the soil and its development. Surplus water percolating through the soil profile transports soluble and suspended materials from the upper to the lower layers. It may also carry away soluble materials in the drainage waters. Thus, percolating water stimulates weathering reactions and helps differentiate soil horizons. Likewise, a deficiency of water is a major factor in determining the characteristics of soils of dry regions. Soluble salts are not leached from these soils, and in some cases they build up to levels that curtail plant growth. Soil profiles in arid and semi-arid regions are also apt to accumulate carbonates and certain types of expansive clays. Considering soils with similar temperature regime, parent material, topography, and age, increasing effective annual precipitation generally leads to increasing clay and organic matter contents, greater acidity, and lower C/Al ratio. The direct influences of climate include, a shallow accumulation of lime in low rainfall areas as caliche, formation of acid soils in humid areas, erosion of soils on steep hillsides, deposition of eroded materials downstream, very intense chemical weathering, leaching, and erosion in warm and humid regions where soil does not freeze. Climate directly affects the rate of weathering and leaching. Soil is said to be formed when detectable layers of clays, organic colloids, carbonates, or soluble salts have been moved downward. Wind moves sand in smaller particles, especially in arid regions where there is little plant cover. The type and amount of precipitation influence soil formation by affecting the movement of ions and particles through the soil, and aid in the development of different soil profiles. Soil profiles are more distinct in wet and cool climates, where organic materials may accumulate, than in wet and warm climates, where organic materials are rapidly consumed. The effectiveness of water in weathering parent rock material depends on seasonal and daily temperature fluctuations. Cycles of freezing and thawing constitute an effective mechanism which breaks up rocks and other consolidated materials. Climate also indirectly influences soil formation through the effects of vegetation cover and biological activity, which modify the rates of chemical reactions in the soil. Topography. The topography, or relief, is characterized by the inclination, elevation, and orientation of the terrain. Topography determines the rate of precipitation or runoff and rate of formation or erosion of the surface soil profile. The topographical setting may either hasten or retard the work of climatic forces. Steep slopes encourage rapid soil loss by erosion and allow less rainfall to enter the soil before running off and hence, little mineral deposition in lower profiles. In semi-arid regions, the lower effective rainfall on steeper slopes also results in less complete vegetative cover, so there is less plant contribution to soil formation. For all of these reasons, steep slopes prevent the formation of soil from getting very far ahead of soil destruction. Therefore, soils on steep terrain tend to have rather shallow, poorly developed profiles in comparison to soils on nearby, more level sites. In swales and depressions where runoff water tends to concentrate, the regolith is usually more deeply weathered and soil profile development is more advanced. However, in the lowest landscape positions, water may saturate the regolith to such a degree that drainage and aeration are restricted. Here, the weathering of some minerals and the decomposition of organic matter are retarded, while the loss of iron and manganese is accelerated. In such low-lying topography, special profile features characteristic of wetland soils may develop. Depressions allow the accumulation of water, minerals and organic matter, and in the extreme, the resulting soils will be saline marshes or peat bogs. Intermediate topography affords the best conditions for the formation of an agriculturally productive soil. Organisms. Soil is the most abundant ecosystem on Earth, but the vast majority of organisms in soil are microbes, a great many of which have not been described. There may be a population limit of around 1 billion cells per gram of soil, but estimates of the number of species vary widely. Estimates range from over 1 million species per gram of soil to 50,000 per gram of soil. The total number of organisms and species can vary widely according to soil type, location, and depth. Plants, animals, fungi, bacteria and humans affect soil formation. Animals, soil mesofauna and microorganisms mix soils as they form burrows and pores, allowing moisture and gases to move about. In the same way, plant roots open channels in soils. Plants with deep taproots can penetrate many meters through the different soil layers to bring up nutrients from deeper in the profile. Plants with fibrous roots that spread out near the soil surface have roots that are easily decomposed, adding organic matter. Microorganisms, including fungi and bacteria, affect chemical exchanges between roots and soil and act as a reserve of nutrients. Humans impact soil formation by removing vegetation cover with erosion as the result. Their tillage also mixes the different soil layers, restarting the soil formation process as less weathered material is mixed with the more developed upper layers. Earthworms, ants and termites mix the soil as they burrow, significantly affecting soil formation. Earthworms ingest soil particles and organic residues, enhancing the availability of plant nutrients in the material that passes through their bodies. They aerate and stir the soil and increase the stability of soil aggregates, thereby assuring ready infiltration of water. As they build mounds, some organisms might transport soil materials from one horizon to another. In general, the mixing activities of animals, sometimes called pedotubation, tends to undo or counteract the tendency of other soil-forming processes that create distinct horizons. Termites and ants may also retard soil profile development by denuding large areas of soil around their nests, leading to increased loss of soil by erosion. Large animals such as gophers, moles, and prairie dogs bore into the lower soil horizons, bringing materials to the surface. Their tunnels are often open to the surface, encouraging the movement of water and air into the subsurface layers. In localized areas, they enhance mixing of the lower and upper horizons by creating, and later refilling, underground tunnels. Old animal burrows in the lower horizons often become filled with soil material from the overlying A horizon, creating profile features known as growth-venas. Vegetation impacts soils in numerous ways. It can prevent erosion caused by excessive rain that might result from surface runoff. Plants shade soils, keeping them cooler and slow evaporation of soil moisture, or conversely, by way of transpiration, plants can cause soils to lose moisture. Plants can form new chemicals that can break down minerals and improve the soil structure. The type and amount of vegetation depends on climate, topography, soil characteristics, and biological factors. Soil factors such as density, depth, chemistry, pH, temperature and moisture greatly affect the type of plants that can grow in a given location. Dead plants and fallen leaves and stems begin their decomposition on the surface. There, organisms feed on them and mix the organic material with the upper soil layers. These added organic compounds become part of the soil formation process. Human activities widely influence soil formation. For example, it is believed that Native Americans regularly set fires to maintain several large areas of prairie grasslands in Indiana and Michigan. In more recent times, human destruction of natural vegetation and subsequent tillage of the soil for crop production has abruptly modified soil formation. Likewise, irrigating an arid region of soil drastically influences the soil-forming factors, as does adding fertilizer and lime to soils of low fertility. Time is a factor in the interactions of all the above. Over time, soils evolve features that are dependent on the interplay of other soil-forming factors. Soil is always changing. It takes about 200 to 1,000 years for a 2.5 cm thick layer of fertile soil to be formed in nature, depending on climate and soil type. For example, recently deposited material from a flood exhibits no soil development because there has not been enough time for the material to form a structure that further defines soil. The original soil surface is buried, and the formation process must begin anew for this deposit. Over a period of between hundreds and thousands of years, the soil will develop a profile that depends on the intensities of biota and climate. While soil can achieve relative stability of its properties for extended periods, the soil life cycle ultimately ends in soil conditions that leave it vulnerable to erosion. Despite the inevitability of soil retrogression and degradation, most soil cycles are long. Soil-forming factors continue to affect soils during their existence, even on a Euro or Euro landscapes that are long-enduring, some for millions of years. Materials are deposited on top or are blown or washed from the surface. With additions, removals and alterations, soils are always subject to new conditions. Whether these are slow or rapid changes depends on climate, topography and biological activity. Physical properties of soils. The physical properties of soils, in order of decreasing importance, are texture, structure, density, porosity, consistency, temperature, color and resistivity. Most of these determine the aeration of the soil and the ability of water to infiltrate and to be held in the soil. Soil texture is determined by the relative proportion of the three kinds of soil particles, called soil separates: sand, silt, and clay. Larger soil structures called PEDs are created from the separates when iron oxides, carbonates, clay, and silica with the organic constituent humus, coat particles and cause them to adhere into larger, relatively stable secondary structures. Soil density, particularly bulk density, is a measure of soil compaction. Soil porosity consists of the part of the soil volume occupied by gases and water. Soil consistency is the ability of soil to stick together. Soil temperature and color are self-defining. Resistivity refers to the resistance to conduction of electric currents and affects the rate of corrosion of metal and concrete structures. The properties may vary through the depth of a soil profile. Texture. The mineral components of soil are sand, silt and clay, and their relative proportions determine a soil's texture. Properties that are influenced by soil texture include porosity, permeability, infiltration, shrink-swell, water-holding capacity, and susceptibility to erosion. In the illustrated USDA textural classification triangle, the only soil in which neither sand, silt nor clay predominates is called loam. While even pure sand, silt or clay may be considered a soil, from the perspective of food production a loam soil with a small amount of organic material is considered ideal. The mineral constituents of a loam soil might be 40% sand, 40% silt and the balance 20% clay by weight. Soil texture affects soil behavior, in particular its retention capacity for nutrients and water. Sand and silt are the products of physical and chemical weathering. Clay, on the other hand, is a product of chemical weathering but often forms as a secondary mineral precipitated from dissolved minerals. It is the specific surface area of soil particles and the unbalanced ionic charges within them that determine their role in the cation exchange capacity of soil, and hence its fertility. Sand is least active, followed by silt. Clay is the most active. Sand's greatest benefit to soil is that it resists compaction and increases porosity. Silt is mineralogically like sand but with its higher specific surface area it is more chemically active than sand. But it is the clay content, with its very high specific surface area and generally large number of negative charges, that gives a soil its high retention capacity for water and nutrients. Clay soils also resist wind and water erosion better than silty and sandy soils, as the particles are bonded to each other. Sand is the most stable of the mineral components of soil. It consists of rock fragments, primarily quartz particles, ranging in size from 2.0 to 0.05 mm in diameter. Silt ranges in size from 0.05 to 0.002 mm. Clay cannot be resolved by optical microscopes as its particles are 0.002 mm or less in diameter. In medium-textured soils, clay is often washed downward through the soil profile and accumulates in the subsoil. Soil components larger than 2.0 mm are classed as rock and gravel and are removed before determining the percentages of the remaining components and the texture class of the soil, but are included in the name. For example, a sandy loam soil with 20% gravel would be called gravelly sandy loam. When the organic component of a soil is substantial, the soil is called organic soil rather than mineral soil. A soil is called organic if mineral fraction is 0% clay and organic matter is 20% or more. Mineral fraction is 0% to 50% clay and organic matter is between 20% and 30%. Mineral fraction is 50% or more clay and organic matter 30% or more. Structure. The clumping of the soil textural components of sand, silt and clay forms aggregates and the further association of those aggregates into larger units forms soil structures called PEDS. The adhesion of the soil textural components by organic substances, iron oxides, carbonates, clays, and silica, and the breakage of those aggregates due to expansion-contraction, freezing-thawing, and wetting-drying cycles, shape soil into distinct geometric forms. These PEDS evolve into units which may have various shapes, sizes and degrees of development. A soil clod, however, is not a PED but rather a mass of soil that results from mechanical disturbance. The soil structure affects aeration, water movement, conduction of heat, plant root growth and resistance to erosion. Water has the strongest effect on soil structure due to its solution and precipitation of minerals and its effect on plant growth. Soil structure often gives clues to its texture, organic matter content, biological activity, past soil evolution, human use, and the chemical and mineralogical conditions under which the soil formed. While texture is defined by the mineral component of a soil and is an innate property of the soil that does not change with agricultural activities, soil structure can be improved or destroyed by the choice and timing of farming practices. Soil structural classes. 1. Types, shape and arrangement of PEDS. A. Platy, PEDS are flattened one atop the other 1 to 10 mm thick. Found in the A horizon of forest soils and lake sedimentation. B. Prismatic and columnar, prism-like PEDS along in the vertical dimension, 10 to 100 mm wide. Prismatic PEDS have flat tops, columnar PEDS have rounded tops. Tend to form in the B horizon in high sodium soil where clay has accumulated. C. Angular and subangular, blocky PEDS are imperfect cubes, 5 to 50 mm, angular have sharp edges, subangular have rounded edges. tend to form in the B horizon where clay has accumulated and indicate poor water penetration. D. Granular in crumb, spheroid PEDS of polyhedrons, 1 to 10 mm, often found in the A horizon in the presence of organic material. Crumb PEDS are more porous and are considered ideal. 2 classes, size of PEDS whose ranges depend upon the above type. A. Very fine or very thin, 1 mm platy and spherical. 5 mm, blocky. 10 mm prism-like. B. Fine or thin, 1 to 2 mm platy, and spherical. 5 to 10 mm blocky. 10 to 20 mm prism-like. C. Medium, 2 to 5 mm platy, granular. 10 to 20 mm blocky. 20 to 50, prism-like. D. Coarse or thick, 5 to 10 mm platy, granular. 20 to 50 mm blocky. 50 to 100 mm prism-like. E. Very coarse or very thick, 10 mm platy, granular. 50 mm, blocky. 100 mm prism-like. 3. Grades, is a measure of the degree of development or cementation within the PEDS that results in their strength and stability. A. Weak cementation allows PEDS to fall apart into the 3 textural constituents, sand, silt and clay. B. Moderate, PEDS are not distinct in undisturbed soil but when removed they break into aggregates, some broken aggregates and little inaggregated material. This is considered ideal. C. Strong, PEDS are distinct before removed from the profile and do not break apart easily. D. Structureless, soil is entirely cemented together in one great mass such as slabs of clay or no cementation at all such, as with sand. At the largest scale, the forces that shape a soil structure result from swelling and shrinkage that initially tend to act horizontally, causing vertically oriented prismatic PEDS. Clayey soil, due to its differential drying rate with respect to the surface, will induce horizontal cracks, reducing columns to blocky PEDS. Roots, rodents, worms, and freezing-thawing cycles further break the PEDS into a spherical shape. At a smaller scale, plant roots extend into voids and remove water and cause the open spaces to increase, and further decrease physical aggregation size. At the same time roots, fungal hyphae and earthworms create microscopic tunnels that break up PEDS. At an even smaller scale, soil aggregation continues as bacteria and fungi exude sticky polysaccharides which bind soil into small PEDS. The addition of the raw organic matter that bacteria and fungi feed upon encourages the formation of this desirable soil structure. At the lowest scale, the soil chemistry affects the aggregation or dispersal of soil particles. The clay particles contain polyvalent cations which give the faces of clay layers a net negative charge. At the same time the edges of the clay plates have a slight positive charge, thereby allowing the edges to adhere to the faces of other clay particles or to flocculate. On the other hand, when monovalent ions such as sodium invade and displace the polyvalent cations, they weaken the positive charges on the edges, while the negative surface charges are relatively strengthened. This leaves a net negative charge on the clay, causing the particles to push apart, and so prevents the flocculation of clay particles into larger assemblages. As a result, the clay disperses and settles into voids between PEDS, causing them to close. In this way the soil aggregation is destroyed and the soil made impenetrable to air and water. Such sodic soil tends to form columnar structures near the surface. Density is the weight per unit volume of an object. Particle density is equal to the mass of solid particles divided by the volume of solid particles. It is the density of only the mineral particles that make up a soil. That is, it excludes pore space and organic material. Soil particle density is typically 2.60 to 2.75 grams per cm3 and is usually unchanging for a given soil. Soil particle density is lower for soils with high organic matter content, and is higher for soils with high Fe oxides content. Soil bulk density is equal to the dry mass of the soil divided by the volume of the soil. That is, it includes airspace and organic materials of the soil volume. A high bulk density is indicative of either soil compaction or high sand content. The bulk density of cultivated loam is about 1.1 to 1.4 gram per centimeter 3. Soil bulk density is highly variable for a given soil. A lower bulk density by itself does not indicate suitability for plant growth due to the influence of soil texture and structure. Soil bulk density is inherently always less than the soil particle density. Porosity, pore space is that part of the bulk volume that is not occupied by either mineral or organic matter but is open space occupied by either gases or water. Ideally, the total pore space should be 50% of the soil volume. The gas space is needed to supply oxygen to organisms decomposing organic matter, humus, and plant roots. Pore space also allows the movement and storage of water and dissolved nutrients. This property of soils effectively compartmentalizes the soil pore space such that many organisms are not in direct competition with one another, which may explain not only the large number of species present, but the fact that functionally redundant organisms can coexist within the same soil. There are 4 categories of pores: very fine pores, 2 AA micrometer, fine pores, 2-20 AA micrometer, medium pores, 20-200 AA micrometer, coarse pores, 200 AA micrometer 0.2 m. In comparison, root hairs are 8 to 12 AA micrometer in diameter. When pore space is less than 30 AA micrometer, the forces of attraction that hold water in place are greater than the gravitational force acting to drain the water. At that point, soil becomes waterlogged and it cannot breathe. For a growing plant, pore size is of greater importance than total pore space. A medium textured loam provides the ideal balance of pore sizes. Having large pore spaces that allow rapid gas and water movement is superior to smaller pore space but has a greater percentage pore space. Soil texture determines the pore space at the smallest scale, but at a larger scale, soil structure has a strong influence on soil, aeration, water infiltration and drainage. Tillage has the short-term benefit of temporarily increasing the number of pores of largest size, but in the end those will be degraded by the destruction of soil aggregation. Structurally, the pores in soil form a homogeneous set of fractals characterized by fractal dimension d less than 3 and linear sizes x. For the clay soil it has been found that d equals 2.7 and x equals 0.150 m. Clay soils have more total pore space, but smaller pores, than sand. Consistency. Consistency is the ability of soil to stick to itself or to other objects and its ability to resist deformation and rupture. It is a rough use in predicting cultivation problems and the engineering of foundations. Consistency is measured at 3 moisture conditions: air dry, moist and wet. And in those conditions the qualities depend upon the clay content. In the wet state, the 2 qualities of stickiness and plasticity are assessed. A soil's resistance to fragmentation and crumbling is assessed in the dry state by rubbing the sample. Its resistance to shearing forces is assessed in the moist state by thumb and finger pressure. Finally, a soil's plasticity is measured in the wet state by molding with the hand. Finally, the cemented consistency depends on cementation by substances other than clay, such as calcium carbonate, silica, oxides and salts, and moisture content has little effect on its assessment. The measures of consistency border on subjective as they employ the feel of the soil in those states. The terms used to describe the soil consistency in 3 moisture states and a last consistency not affected by the amount of moisture are as follows: consistency of dry soil, loose, soft, slightly hard, hard, very hard, extremely hard; consistency of moist soil, loose, very friable, friable, firm, very firm, extremely firm; consistency of wet soil, non-sticky, slightly sticky, sticky, very sticky. Non-plastic, slightly plastic, plastic, very plastic; consistency of cemented soil, weakly cemented, strongly cemented, indurated, Soil consistency is useful in estimating the ability of soil to support buildings and roads. More precise measures of soil strength are often made prior to construction. Temperature. Soil temperature depends on the ratio of the energy absorbed to that lost. Soil has a temperature range between -20 to 60 degrees Celsius. Soil temperature regulates seed germination, plant and root growth and the availability of nutrients. Below 50 cm, soil temperature seldom changes and can be approximated by adding 1.8 degrees Celsius to the mean annual air temperature. Soil temperature has important seasonal, monthly and daily variations. Fluctuations in soil temperature are much lower with increasing soil depth. Heavy mulching can slow the warming of soil, and, at the same time, reduce fluctuations in surface temperature. Most often, agricultural activities must adapt to soil temperatures by maximizing germination and growth by timing of planting, optimizing use of anhydrous ammonia by applying to soil below 10 degrees Celsius, preventing heaving and thawing due to frosts from damaging shallow-rooted crops, preventing damage to desirable soil structure by freezing of saturated soils, improving uptake of phosphorus by plants. Otherwise soil temperatures can be raised by drying soils or the use of clear plastic mulches. Organic mulches slow the warming of the soil. There are various factors that affect soil temperature, such as water content, soil color, and relief, and soil cover. The color of the ground cover and its insulating properties have a strong influence on soil temperature. Whiter soil tends to have a higher albedo than blacker soil cover, which encourages whiter soils to have cooler soil temperatures. The specific heat of soil is the energy required to raise the temperature of soil by 1 degree Celsius. The specific heat of soil increases as water content increases, since the heat capacity of water is greater than that of dry soil. The specific heat of pure water is 1 calorie per gram. The specific heat of dry soil is 0.2 calories per gram and the specific heat of wet soil is 0.2 to 1 calories per gram. Also, tremendous energy is required and dissipated to evaporate water. As such, wet soil usually warms more slowly than dry soil. Wet surface soil is typically 3 to 6 degrees Celsius colder than dry surface soil. Soil heat flux refers to the conduction of energy in response to a temperature gradient. The heat flux density is the amount of energy that flows through soil per unit area per unit time. Where is the local heat flux, WAM-R2, is the material's conductivity, WAM-R1 Car1, is the temperature gradient, CAM-R1. The thermal conductivity is often treated as a constant, though this is not always true. While the thermal conductivity of a material generally varies with temperature, the variation can be small over a significant range of temperatures for some common materials. In anisotropic materials, the thermal conductivity typically varies with orientation. In this case is represented by a second-order tensor. In non-uniform materials, varies with spatial location. For soil, thermal conductivity also depends on mineral composition, water content, and bulk density. Compact and wet soils have a higher thermal conductivity than loose and dry soils. For many simple applications, Fourier's law is used in its one-dimensional, x-direction form. Color. Soil color is often the first impression one has when viewing soil. Striking colors and contrasting patterns are especially noticeable. The Red River carries sediment eroded from extensive reddish soils like Port Silt Loam in Oklahoma. The Yellow River in China carries yellow sediment from eroding loess soils. Mollisls in the Great Plains of North America are darkened and enriched by organic matter. Podsols in boreal forests have highly contrasting layers due to acidity and leaching. In general, color is determined by the organic matter content, drainage conditions, and degree of oxidation. Soil color, while easily discerned, has little use in predicting soil characteristics. Arizona Master Gardener Manual. Cooperative Extension, College of Agriculture, University of Arizona. PA Chapter 2, pages 4-8. retrieved May 27, 2013. It is of use in distinguishing boundaries within a soil profile, determining the origin of a soil's parent material, as an indication of wetness and waterlogged conditions, and as a qualitative means of measuring organic, salt and carbonate contents of soils. Color is recorded in the Munsell color system as, for instance, 10 years 3/4. Soil color is primarily influenced by soil mineralogy. Many soil colors are due to various iron minerals. The development and distribution of color in a soil profile result from chemical and biological weathering, especially redox reactions. As the primary minerals in soil parent material weather, the elements combine into new and colorful compounds. Iron forms secondary minerals of a yellow or red color, organic matter decomposes into black and brown compounds, and manganese, sulfur and nitrogen can form black mineral deposits. These pigments can produce various color patterns within a soil. Aerobic conditions produce uniform or gradual color changes, while reducing environments result in rapid color flow with complex, mottled patterns and points of color concentration. Resistivity. Soil resistivity is a measure of a soil's ability to retard the conduction of an electric current. The electrical resistivity of soil can affect the rate of galvanic corrosion of metallic structures in contact with the soil. Higher moisture content or increased electrolyte concentration can lower resistivity and increase conductivity, thereby increasing the rate of corrosion. Soil resistivity values typically range from about 2 to 1000 AIM, but more extreme values are not unusual. Soil water. Water affects soil formation, structure, stability and erosion, but is of primary concern with respect to plant growth. Water is essential to plants for 4 reasons. It constitutes 80%-95% of the plant's protoplasm. It is essential for photosynthesis. It is the solvent in which nutrients are carried to, into and throughout the plant. It provides the turgidity by which the plant keeps itself in proper position. In addition, water alters the soil profile by dissolving and redepositing minerals, often at lower levels, and possibly leaving the soil sterile in the case of extreme rainfall and drainage. In a loam soil, solids constitute half the volume, gas 1/4 of the volume, and water 1/4 of the volume, of which only half will be available to most plants. A flooded field will drain the gravitational water under the influence of gravity until water's adhesive and cohesive forces resist further drainage and it finally reaches field capacity. Plants must apply suction to draw water from a soil. When soil becomes too dry, the available water is used up and the remaining moisture is unavailable water as the plant cannot produce sufficient suction. A plant must produce suction that increases from 0 for a flooded field to 1/3 bar at field dry condition. At 15 bar suction, wilting %, plants begin to die. Water moves in soil under the influence of gravity, osmosis and capillarity. When water enters the soil, it displaces air from some of the pores, since air content of a soil is inversely related to its water content. As a plant grows, its roots remove water from the largest pores first. Soon the larger pores hold only air, and the remaining water is found only in the intermediate and smallest sized pores. The water in the smallest pores is so strongly held on particle surfaces that plant roots cannot pull it away. Consequently, not all soil water is available to plants. The rate at which a soil can absorb water depends on the soil and its other conditions. As a plant grows, its roots remove water from the largest pores first. Soon the larger pores hold only air, and the remaining water is found only in the intermediate and smallest sized pores. The water in the smallest pores is so strongly held on particle surfaces that plant roots cannot pull it away. Consequently, not all soil water is available to plants. When saturated, the soil may lose nutrients as the water drains. Water moves in a drained field under the influence of pressure where the soil is locally saturated and of capillarity pull. Most plant water needs are supplied from the suction of evaporation from plant leaves and 10% is supplied by suction created by osmotic pressure. Plant roots must seek out water. Insufficient water will damage the yield of a crop. Most of the available water is used in transpiration to pull nutrients into the plant. Water retention forces. Water is retained in a soil when the adhesive force of attraction of water's hydrogen atoms for the oxygen of soil particles and the cohesive forces water's hydrogen feels for other water's oxygen atoms are stronger than the forces that might pull it from the soil. When a field is flooded, the airspace is displaced by water. The field will drain under the force of gravity until it reaches what is called field capacity, at which point the smallest pores are filled with water and the largest with water and gases. The total amount of water held when field capacity is reached is a function of the specific surface area of the soil particles. As a result, high clay and high organic soils have higher field capacities. The total force required to pull or push water out of soil is termed suction and usually expressed in units of bars, which is just a little less than 1 atmosphere pressure. Alternatively, the terms tension, or moisture potential may be used. Moisture classification. The forces with which water is held in soils determine its availability to plants. Forces of adhesion hold water strongly to mineral and humus surfaces and less strongly to itself by cohesive forces. A plant's root may penetrate a very small volume of water that is adhering to soil and be initially able to draw in water that is only lightly held by the cohesive forces. But as the droplet is drawn down, the forces of adhesion of the water for the soil particles make reducing the volume of water increasingly difficult until the plant cannot produce sufficient suction to use the remaining water. The remaining water is considered unavailable. The amount of available water depends upon the soil texture and humus amounts and the type of plant attempting to use the water. Cacti, for example, can produce greater suction than can agricultural crop plants. The following description applies to a loam soil and agricultural crops. When a field is flooded, it is said to be saturated and all available airspace is occupied by water. The suction required to draw water into a plant root is zero. As the field drains under the influence of gravity, the suction a plant must produce to use such water increases to 1/3 a bar. At that point, the soil is said to have reached field capacity, and plants that use the water must produce increasingly higher suction, finally up to 15 a bar. At 15 a bar suction, the soil water amount is called wilting percent. At that suction the plant cannot sustain its water needs as water is still being lost from the plant by transpiration. The plant's turgidity is lost, and it wilts. The next level, called air dry, occurs at 1000 a bar suction. Finally the oven dry condition is reached at 10,000 a bar suction. All water below wilting percentage is called unavailable water. Soil moisture content. When the soil moisture content is optimal for plant growth, the water in the large and intermediate-sized pores can move about in the soil and can easily be used by plants. The amount of water remaining in a soil drained to field capacity and the amount that is available are functions of the soil type. Sandy soil will retain very little water, while clay will hold the maximum amount. The time required to drain a field from flooded condition for a clay loam that begins at 43% water by weight to a field capacity of 21.5% is 6 days, whereas a sand loam that is flooded to its maximum of 22% water will take 2 days to reach field capacity of 11.3% water. The available water for the clay loam might be 11.3% whereas for the sand loam it might be only 7.9% by weight. The above are average values for the soil textures as the percentage of sand, silt and clay vary within the listed soil textures. Water flow in soils. Water moves through soil due to the force of gravity, osmosis and capillarity. At 0 to 1/3 bar suction, water moves through soil due to gravity. This is called saturated flow. At higher suction, water movement is called unsaturated flow. Water infiltration into soil is controlled by 6 factors: soil texture, soil structure. Fine-textured soils with granular structure are most favorable to infiltration of water. The amount of organic matter. Coarse matter is best and if on the surface helps prevent the destruction of soil structure and the creation of crusts. Depth of soil to impervious layers such as hard pans or bedrock, the amount of water already in the soil, soil temperature. Warm soils take in water faster while frozen soils may not be able to absorb depending on the type of freezing. Water infiltration rates range from 0.25 cm per hour for high clay soils to 2.5 cm per hour for sand and well-stabilized and aggregated soil structures. Water flows through the ground unevenly, called gravity fingers, because of the surface tension between water particles. Tree roots create paths for rainwater flow through soil by breaking those soil including clay layers. One study showed roots increasing infiltration of water by 153% and another study showed an increase by 27 times. Flooding temporarily increases soil permeability in riverbeds, helping recharge aquifers. Saturated flow: once soil is completely wetted, any more water will move downward, or percolate, carrying with it clay, humus and nutrients, primarily cations, out of the range of plant roots and result in acid soil conditions. In order of decreasing solubility, the leached nutrients are calcium, magnesium, sulfur, potassium. Depending upon soil composition, nitrogen. Usually little, unless nitrate fertilizer was applied recently, phosphorus. Very little as its forms in soil are of low solubility. In the United States, percolation water due to rainfall ranges from 0 inches just east of the Rocky Mountains to 20 or more inches in the Appalachian Mountains and the north coast of the Gulf of Mexico. Unsaturated flow: at suctions less than 1/3 bar, water moves in all directions via unsaturated flow at a rate that is dependent on the square of the diameter of the water-filled pores. Water is pushed by pressure gradients from the point of its application where it is saturated locally, and pulled by capillary action due to the adhesion force of water to the soil solids, producing a suction gradient from wet towards drier soil. Doubling the diameter of the pores increases the flow rate by a factor of 4. Large pores drained by gravity and not filled with water do not greatly increase the flow rate for unsaturated flow. Water flow is primarily from coarse textured soil into fine textured soil and is slowest in fine textured soils such as clay. Water uptake by plants: of equal importance to the storage and movement of water in soil is the means by which plants acquire it and their nutrients. 90% of water is taken up by plants as passive absorption caused by the pulling force of water evaporating from the long column of water that leads from the plant's roots to its leaves. In addition, the high concentration of salts within plant roots creates an osmotic pressure gradient that pushes soil water into the roots. Osmotic absorption becomes more important during times of low water transpiration caused by lower temperatures or high humidity. It is the process that causes guttation. Root extension is vital for plant survival. A study of a single winter rye plant grown for 4 months in 1 cubic foot of loam soil showed that the plant developed 13,800,000 roots, a total of 385 miles in length and 2,550 square feet in surface area, and 14 billion hair roots of 6,600 miles total length and 4,320 square feet total area, for a total surface area of 6,870 square feet. The total surface area of the loam soil was estimated to be 560,000 square feet. In other words, the roots were in contact with only 1.2% of the soil. Roots must seek out water as the unsaturated flow of water in soil can move only at a rate of up to 2.5 cm per day. As a result, they are constantly dying and growing as they seek out high concentrations of soil moisture. Insufficient soil moisture to the point of wilting will cause permanent damage and crop yields will suffer. When grain sorghum was exposed to soil suction as low as 13.0 bar during the seed head emergence through bloom and seed set stages of growth, its production was reduced by 34%. Consumptive use and water efficiency: only a small fraction of the water used by a plant is held within the plant. The majority is ultimately lost via transpiration, while evaporation from the soil surface is also substantial. Transpiration plus evaporative soil moisture loss is called evapotranspiration. Evapotranspiration plus water held in the plant totals consumptive use, which is nearly identical to evapotranspiration. The total water used in an agricultural field includes runoff, drainage and consumptive use. The use of loose mulches will reduce evaporative losses for a period after a field is irrigated, but in the end the total evaporative loss will approach that of an uncovered soil. The benefit from mulch is to keep the moisture available during the seedling stage. Water use efficiency is measured by transpiration ratio, which is the ratio of the total water transpired by a plant to the dry weight of the harvested plant. Transpiration ratios for crops range from 300 to 700. For example, alfalfa may have a transpiration ratio of 500 and as a result 500 kilograms of water will produce only a kilogram of dry alfalfa. Soil atmosphere. The atmosphere of soil is radically different from the atmosphere above. The consumption of oxygen, by microbes and plant roots and their release of carbon dioxide, decrease oxygen and increase carbon dioxide concentration. Atmospheric CO2 concentration is 0.04%, but in the soil pore space it may range from 10 to 100 times that level. At extreme levels CO2 is toxic. In addition, the soil voids are saturated with water vapor. Adequate porosity is necessary not just to allow the penetration of water but also to allow gases to diffuse in and out. Movement of gases is by diffusion from high concentrations to lower. Oxygen diffuses in and is consumed and excess levels of carbon dioxide diffuse out with other gases as well as water. Soil texture and structure strongly affect soil porosity and gas diffusion. Platy and compacted soils impede gas flow, and a deficiency of oxygen may encourage anaerobic bacteria to reduce nitrate to the gases N2, N2O, and NO, which are then lost to the atmosphere. Aerated soil is also a net sink of methane CH4 but a net producer of greenhouse gases when soils are depleted of oxygen and subject to elevated temperatures. Colloidal and chemical properties. The chemistry of soil determines the availability of nutrients, the health of microbial populations, and its physical properties. In addition, soil chemistry also determines its corrosivity, stability, and ability to absorb pollutants and to filter water. It is the surface chemistry of clay and humus colloids that determines soil's chemical properties. A EuroOEA colloid is a small, insoluble, non-diffusible particle larger than a molecule but small enough to remain suspended in a fluid medium without settling. Most soils contain organic colloidal particles called humus as well as the inorganic colloidal particles of clays. The very high specific surface area of colloids and their net negative charges gives soil its great ability to hold and release cations in what is referred to as cation exchange. Cation exchange capacity is the amount of exchangeable cations per unit weight of dry soil and is expressed in terms of molar equivalents of hydrogen ion per 100 grams of soil. Mineral colloids. Soil clays. Due to its high specific surface area and its unbalanced negative charges, clay is the most active mineral component of soil. It is a colloidal and most often a crystalline material. In soils, clay is defined in a physical sense as any mineral particle less than 2 a micrometer in effective diameter. Chemically, clay is a range of minerals with certain reactive properties. Clay is also a soil textural class. Many soil minerals, such as gypsum, carbonates, or quartz, are small enough to be classified physically as clay but chemically do not afford the same utility as do clay minerals. Clay was once thought to be very small particles of quartz, feldspar, mica, hornblende or augite, but it is now known to be a precipitate with a mineralogical composition that is dependent on but different from its parent materials and is classed as a secondary mineral. The type of clay that is formed is a function of the parent material and the composition of the minerals in solution. Clay minerals continue to be formed as long as the soil exists. Mica-based clays result from a modification of the primary mica mineral in such a way that it behaves and is classed as a clay. Most clays are crystalline, but some are amorphous. The clays of a soil are a mixture of the various types of clay, but one type predominates. Most clays are crystalline and most are made up of 3 or 4 planes of oxygen held together by planes of aluminium and silicon by way of ionic bonds that together form a single layer of clay. The spatial arrangement of the oxygen atoms determines clay's structure. Half of the weight of clay is oxygen, but on a volume basis oxygen is 90%. The layers of clay are sometimes held together through hydrogen bonds or potassium bridges and as a result swell less in the presence of water. Other clays, such as montmorillonite, have layers that are loosely attached and will swell greatly when water intervenes. There are three groups of clays: crystalline aluminosilica clays, montmorillonite, illite, vermiculite, chlorite, kaolinite. Amorphous clays, young mixtures of silica and alumina 3, which have not had time to form regular crystals. Sesquioxide clays, old, highly leached clays which result in oxides of iron, aluminium and titanium. Aluminosilica clays are characterized by their regular crystalline structure. Oxygen in ionic bonds with silicon forms a tetrahedral coordination which in turn forms sheets of silica. Two sheets of silica are bonded together by a plane of aluminium which forms an octahedral coordination, called alumina, with the oxygens of the silica sheet above and that below it. Hydroxyl ions sometimes substitute for oxygen. During the clay formation process, Al3+ may substitute for C4+, and as much as 1/4 of the aluminium Al3+ may be substituted by Zn2+, Mg2+, or Fe2+. The substitution of lower valence cations for higher valence cations gives clay a net negative charge that attracts and holds soil cations, some of which are of value for plant growth. Isomorphic substitution occurs during the clay's formation and does not change with time. Montmorillonite clay is made of 4 planes of oxygen with 2 silicon and 1 central aluminium plane intervening. The aluminosilicate montmorillonite clay is said to have a 2:1 ratio of silicon to aluminium. The 7 planes together form a single layer of montmorillonite. The layers are weakly held together and water may intervene, causing the clay to swell up to 10 times its dry volume. It occurs in soils which have had little leaching, hence it is found in arid regions. The entire surface is exposed and available for surface reactions and it has a high cation exchange capacity. Illite is a 2:1 clay similar in structure to montmorillonite but has potassium bridges between the clay layers and the degree of swelling depends on the degree of weathering of the potassium. The active surface area is reduced due to the potassium bonds. Illite originates from the modification of mica, a primary mineral. It is often found together with montmorillonite and its primary minerals. It has moderate CEC. Vermiculite is a mica-based clay similar to illite, but the layers of clay are held together more loosely by hydrated magnesium and it will swell, but not as much as does montmorillonite. It has very high CEC. Chlorite is similar to vermiculite, but the loose bonding by occasional hydrated magnesium is replaced by a hydrated magnesium sheet, firmly bonding the planes above and below it. It has 2 planes of silicon, 1 of aluminium and 1 of magnesium. Hence it is a 2:2 clay. Chlorite does not swell and it has low CEC. Kaolinite is very common, more common than montmorillonite in acid soils. It has 1 silica and 1 alumina sheet per layer. Hence it is a 1:1 type clay. 1 layer of oxygen is replaced with hydroxyls, which produces strong hydrogen bonds to the oxygen in the next layer of clay. As a result, kaolinite does not swell in water and has a low specific surface area, and as almost no isomorphic substitution has occurred it has a low CEC. Where rainfall is high, acid soils selectively leach more silica than alumina from the original clays, leaving kaolinite. Even heavier weathering results in sesquioxide clays. Amorphous clays are young, and commonly found in volcanic ash. They are mixtures of alumina and silica which have not formed the ordered crystal shape of aluminosilica clays which time would provide. The majority of their negative charges originates from hydroxyl ions, which can gain or lose a hydrogen ion in response to soil pH, and hence buffer the soil pH. They may have either a negative charge provided by the attached hydroxyl ion, which can attract a cation, or lose the hydrogen of the hydroxyl to solution and display a positive charge which can attract anions. As a result they may display either high CEC, in an acid soil solution, or high anion exchange capacity, in a basic soil solution. Sesquioxide clays Sesquioxide clays are a product of heavy rainfall that has leached most of the silica and alumina from aluminosilica clay, leaving the less soluble oxides of iron Fe2O3 and iron hydroxide 3, and aluminium hydroxide 3. It takes hundreds of thousands of years of leaching to create sesquioxide clays. Sesqui is Latin for 1 and 1/2. There are 3 parts oxygen to 2 parts iron or aluminium. Hence the ratio is 1 and 1/2. They are hydrated and act as either amorphous or crystalline. They are not sticky and do not swell, and soils high in them behave much like sand and can rapidly pass water. They are able to hold large quantities of phosphates. Sesquioxides have low CEC. Such soils range from yellow to red in color. Such clays tend to hold phosphorus tightly, rendering them unavailable for absorption by plants. Organic colloids. Humus is the penultimate state of decomposition of organic matter. While it may linger for 1,000 years, on the larger scale of the age of the other soil components, it is temporary. It is composed of the very stable lignins and complex sugars, proteins, waxes, and fats. Its chemical assay is 60% carbon, 5% nitrogen, some oxygen and the remainder hydrogen, sulfur, and phosphorus. On a dry weight basis, the CEC of humus is many times greater than that of clay. Carbon and terra preta. In the extreme environment of high temperatures and the heavy leaching caused by the heavy rain of tropical rainforests, the clay and organic colloids are largely destroyed. The heavy rain washes the aluminosilicate clays from the soil, leaving only sesquioxide clays of low CEC. The high temperatures and humidity allow bacteria and fungi to virtually dissolve any organic matter on the rainforest floor overnight, and much of the nutrients are volatilized or leached from the soil and lost. However, carbon in the form of charcoal is far more stable than soil colloids and is capable of performing many of the functions of the soil colloids of subtropical soils. Soil containing substantial quantities of charcoal, of an anthropogenic origin, is called terra preta. Research into terra preta is still young but is promising. Fallow periods on the Amazonian dark earths can be as short as 6 months, whereas fallow periods on oxysols are usually 8 to 10 years long. Cation and anion exchange. Cation exchange, between colloids and soil water, buffers soil pH, alters soil structure, and purifies percolating water by adsorbing cations of all types, both useful and harmful. The negative charges on a colloid particle make it able to hold cations to its surface. The charges result from 4 sources. Isomorphous substitution occurs in clay when lower valence cations substitute for higher valence cations in the crystal structure. Substitutions in the outermost layers are more effective than for the innermost layers, as the charge strength drops off as the square of the distance. The net result is a negative charge. Edge of clay oxygen atoms are not in balance ionically, as the tetrahedral and octahedral structures are incomplete at the edges of clay. Hydroxyls may substitute for oxygens of the silica layers. When the hydrogens of the clay hydroxyls are ionized into solution, they leave the oxygen with a negative charge. Hydrogens of humus hydroxyl groups may be ionized into solution, leaving an oxygen with a negative charge. Cations held to the negatively charged colloids resist being washed downward by water and out of reach of plant roots, thereby preserving the fertility of soils in areas of moderate rainfall and low temperatures. There is a hierarchy in the process of cation exchange on colloids, as they differ in the strength of adsorption by the colloid and hence their ability to replace one another. If present in equal amounts in the soil-water solution, Al3+ replaces H+ replaces Ca2+ replaces Mg2+ replaces K+, same as NH4+ replaces Na+. If one cation is added in large amounts, it may replace the others by the sheer force of its numbers. This is largely what occurs with the addition of fertilizer. As the soil solution becomes more acidic, the other cations bound to colloids are pushed into solution. This is caused by the ionization of hydroxyl groups on the surface of soil colloids in what is described as pH-dependent charges. Unlike permanent charges developed by isomorphous substitution, pH-dependent charges are variable and increase with increasing pH. As a result, Those cations can be made available to plants but are also able to be leached from the soil, possibly making the soil less fertile. Plants will excrete H+ into the soil and by the means, push cations off the colloids, thus making those absorbable by the plant. Cation exchange capacity. Cation exchange capacity should be thought of as the soil's ability to remove cations from the soil-water solution and sequester those to be exchanged later as the plant roots release hydrogen ions to the solution. CEC is the amount of exchangeable hydrogen cation that will combine with 100 grams dry weight of soil and whose measure is 1 milliequivalents per 100 grams of soil. Hydrogen ions have a single charge and 1,000th of a gram of hydrogen ions per 100 grams dry soil gives a measure of 1 milliequivalent of hydrogen ion. Calcium, with an atomic weight 40 times that of hydrogen and with a valence of 2, converts to X1 milliequivalent equals 20 milliequivalents of hydrogen ion per 100 grams of dry soil or 20 mx/100 Ag. The modern measure of CEC is expressed as centimoles of positive charge per kilogram of oven-dry soil. Most of the soil's CEC occurs on clay and humus colloids, and the lack of those in hot, humid, wet climates, due to leaching and decomposition respectively, explains the relative sterility of tropical soils. Live plant roots also have some CEC. Anion exchange capacity. Anion exchange capacity should be thought of as the soil's ability to remove anions from the soil-water solution and sequester those for later exchange as the plant roots release carbonate anions to the soil-water solution. Those colloids which have low CEC tend to have some AEC. Amorphous and sesquioxide clays have the highest AEC, followed by the iron oxides. Levels of AEC are much lower than for CEC. Phosphates tend to be held at anion exchange sites. Iron and aluminum hydroxide clays are able to exchange their hydroxide anions for other anions. The order reflecting the strength of anion adhesion is as follows: H2PO4 replaces SO42 replaces NO3 replaces Cl. The amount of exchangeable anions is of a magnitude of tenths to a few milliequivalents per 100 Ag dry soil. As pH rises, there are relatively more hydroxyls, which will displace anions from the colloids and force them into solution and out of storage. Hence AEC decreases with increasing pH. Soil reaction. Soil reactivity is expressed in terms of pH and is a measure of the acidity or alkalinity of the soil. More precisely, it is a measure of hydrogen ion concentration in an aqueous solution and ranges in values from 0 to 14, but practically speaking for soils, pH ranges from 3.5 to 9.5, as pH values beyond those extremes are toxic to life forms. Soil pH, at 25 degrees Celsius, an aqueous solution that has a pH of 3.5 has 10 to 3.5 moles H+ per liter of solution. A pH of 7, defined as neutral, has 10 to 7 moles hydrogen ions per liter of solution and also 10 to 7 moles of OH per liter. Since the two concentrations are equal, they are said to neutralize each other. A pH of 9.5 has 10 to 9.5 moles hydrogen ions per liter of solution. A pH of 3.5 has 1 million times more hydrogen ions per liter than a solution with pH of 9.5 and is more acidic. The effect of pH on a soil is to remove from the soil or to make available certain ions. Soils with high acidity tend to have toxic amounts of aluminium and manganese. Plants which need calcium need moderate alkalinity, but most minerals are more soluble in acid soils. Soil organisms are hindered by high acidity, and most agricultural crops do best with mineral soils of pH 6.5 and organic soils of pH 5.5. In high rainfall areas, soils tend to acidity as the basic cations are forced off the soil colloids by the mass action of hydrogen ions from the rain as those attached to the colloids. High rainfall rates can then wash the nutrients out, leaving the soil sterile. Once the colloids are saturated with H+, the addition of any more hydrogen ions or aluminum hydroxyl cations drives the pH even lower as the soil has been left with no buffering capacity. In areas of extreme rainfall and high temperatures, the clay and humus may be washed out, further reducing the buffering capacity of the soil. In low rainfall areas, Enleached calcium pushes pH to 8.5, and with the addition of exchangeable sodium, soils may reach pH 10. Beyond a pH of 9, plant growth is reduced. High pH results in low micronutrient mobility, but water-soluble chelates of those nutrients can supply the deficit. Sodium can be reduced by the addition of gypsum, as calcium adheres to clay more tightly than does sodium, causing sodium to be pushed into the soil-water solution, where it can be washed out by an abundance of water. Base saturation percentage: there are acid-forming cations and there are base-forming cations. The fraction of the base-forming cations that occupy positions on the soil colloids is called the base saturation percentage. If a soil has a CEC of 20 mech and 5 mech are aluminium and hydrogen cations, the remainder of positions on the colloids are assumed occupied by base-forming cations, so that the percentage base saturation is 15/20 x 100% equals 75%. When the soil pH is 7, base saturation is 100% and there are no hydrogen ions stored on the colloids. Base saturation is almost in direct proportion to pH. It is of use in calculating the amount of lime needed to neutralize an acid soil. The amount of lime needed to neutralize a soil must take account of the amount of acid-forming ions on the colloids, not just those in the soil-water solution. The addition of enough lime to neutralize the soil-water solution will be insufficient to change the pH, as the acid-forming cations stored on the soil colloids will tend to restore the original pH condition as they are pushed off those colloids by the calcium of the added lime. Buffering of soils. The resistance of soil to changes in pH as a result of the addition of acid or basic material is a measure of the buffering capacity of a soil and increases as the CEC increases. Hence, pure sand has almost no buffering ability, while soils high in colloids have high buffering capacity. Buffering occurs by cation exchange and neutralization. The addition of a small amount highly basic aqueous ammonia to a soil will cause the ammonium to displace hydrogen ions from the colloids, and the end product is water and colloidally fixed ammonium, but no permanent change overall in soil pH. The addition of a small amount of lime, CaCO3, will displace hydrogen ions from the soil colloids, causing the fixation of calcium to colloids and the evolution of CO2 and water, with no permanent change in soil pH. The addition of carbonic acid will displace calcium from colloids, as hydrogen ions are fixed to the colloids, evolving water and slightly alkaline highly soluble calcium bicarbonate, which will then precipitate as lime and water at a lower level in the soil profile, with the result of no permanent change in soil pH. All of the above are examples of the buffering of soil pH. The general principle is that an increase in a particular cation in the soil-water solution will cause that cation to be fixed to colloids, and a decrease in solution of that cation will cause it to be withdrawn from the colloid and moved into solution. The degree of buffering is limited by the CEC of the soil. The greater the CEC, the greater the buffering capacity of the soil. Nutrients. 16 nutrients are essential for plant growth and reproduction. They are carbon, hydrogen, oxygen, nitrogen, phosphorus, potassium, sulfur, calcium, magnesium, iron, boron, manganese, copper, zinc, molybdenum, and chlorine. Nutrients required for plants to complete their life cycle are considered essential nutrients. With the exception of carbon, hydrogen and oxygen, which are supplied by carbon dioxide and water, the nutrients derive originally from the mineral component of the soil. Although minerals are the origin of those nutrients, the organic component is the reservoir of the majority of readily available plant nutrients. The application of finely ground minerals, feldspar and apatite, to soil does not provide the necessary amounts of potassium and phosphorus for good plant growth. Nitrogen is the primary limiting nutrient. Phosphorus is second to nitrogen as the primary nutrient for plants, animals and microorganisms. Nearly all plant nutrients are taken up in ionic forms from the soil solution as cations or as anions. Plants release bicarbonate and hydroxyl anions from their roots to allow absorption of nutrient anions or hydrogen cations in exchange for cation forms of nutrients. As a result, nutrient ions freed from sequestration on colloids are released into soil solution. Nitrogen is available in soil organic material but is unusable by plants until it is made available by that material's decomposition by microorganisms into cation or anion forms. Plant nutrition involves biological, physical, and chemical processes. The tiniest colloidal-sized particles, both clay and humus, tend to attract or adsorb oppositely charged ions from the soil solution and hold them as exchangeable ions. Through ion exchange, elements such as calcium and potassium are released from this state of electrostatic adsorption on colloidal surfaces and escape into the soil solution. Generally, plant roots can readily absorb all of the nutrients from the soil solution, provided there is enough oxygen gas in the soil to support root metabolism. The bulk of most nutrient elements is held in the structural framework of primary and secondary minerals and organic matter. The structural framework of primary minerals and organic matter is very slowly available to plants. The colloidal fraction has a structural framework of clay and humus that is less slowly available to plants. The adsorbed fraction has ions held on colloidal surfaces that are moderately available. And the soil solution fraction has ions that are freely available for absorption by plant roots. Gram for gram, the capacity of humus to hold nutrients and water is far greater than that of clay. All in all, small amounts of humus may remarkably increase the soil unregistered trademark's capacity to promote plant growth. Mechanism of nutrient uptake. To be taken up by a plant, a nutrient element must be in a soluble form and must be located at the root surface. Often, parts of a root are in such intimate contact with soil particles that a direct exchange may take place between nutrient ions adsorbed on the surface of the soil colloids and hydrogen ions from the surface of root cell walls. In any case, the supply of nutrients in contact with the root would soon be depleted. There are, however, three basic mechanisms by which the concentration of nutrient ions at the root surface is maintained. All the nutrients with the exception of carbon are taken up by the plant through its roots. All those brought into the roots, with the exception of hydrogen, are taken up in the form of ions. Nutrient levels in plants are typically maintained by three principal mechanisms by which nutrient ions dissolved in the soil solution are brought into contact with plant roots: mass flow, diffusion, root interception. All three mechanisms operate simultaneously, but one mechanism or another may be most important for a particular nutrient. For example, in the case of calcium, which is generally plentiful in the soil solution, mass flow alone can usually bring sufficient amounts to the root surface. However, in the case of phosphorus, diffusion is needed to supplement mass flow because the soil solution is very low in this element in comparison to the amounts needed by plants. For the most part, nutrient ions must travel some distance in the soil solution to reach the root surface. This movement can take place by mass flow, as when dissolved nutrients are carried along with the soil water flowing toward a root that is actively drawing water from the soil. In this type of movement, the nutrient ions are somewhat analogous to leaves floating down a stream. In addition, nutrient ions continually move by diffusion from areas of greater concentration toward the nutrient-depleted areas of lower concentration around the root surface. By this means, plants can continue to take up nutrients even at night, when water is only slowly absorbed into the roots. Finally, root interception comes into play as roots continually grow into new, undepleted soil. Because nutrient uptake is an active metabolic process, conditions that inhibit root metabolism may also inhibit nutrient uptake. Examples of such conditions include excessive soil water content or soil compaction resulting in poor soil aeration, excessively high or low soil temperatures, and above-ground conditions that result in low translocation of sugars to plant roots. A maize plant will use 1 quart of water per day at the height of its growing season. In the above table, phosphorus and potassium nutrients move more by diffusion than they do by mass flow in water solution, as they are rapidly taken up by the roots, creating a concentration of almost zero near the roots. The very steep concentration gradient is of greater influence in the movement of those ions than is the movement of those by mass flow. The movement by mass flow requires the transpiration of water from the plant, causing water and solution ions to also move toward the roots. Movement by root interception is slowest as the plants must extend their roots. Plants move ions out of their roots in an effort to move nutrients in from the soil. Hydrogen H+ is exchanged for cations, and carbonate and hydroxide anions are exchanged for nutrient anions. Plants derive most of their anion nutrients from decomposing organic matter, which holds 95% of the nitrogen, 5 to 60% of the phosphorus and 80% of the sulfur. As plant roots remove nutrients from the soil-water solution, nutrients are added to the soil water as other ions move off of clay and humus, are added from the decomposition of soil minerals, and are released by the decomposition of organic matter. Where crops are produced, the replenishment of nutrients in the soil must be augmented by the addition of fertilizer or organic matter. Carbon. Plants obtain their carbon from atmospheric carbon dioxide. A plant's weight is 45% carbon. Elementally, carbon is 50% of plant material. Plant residues have a carbon-to-nitrogen ratio of 50:1. As the soil organic material is digested by arthropods and microorganisms, the CN decreases as the carbonaceous material is metabolized and carbon dioxide is released as a byproduct and finds its way out of the soil and into the atmosphere. The nitrogen, however, is sequestered in the bodies of the living matter of those organisms and so it builds up in the soil. Normal CO2 concentration in the atmosphere is 0.03%, which is probably the factor limiting plant growth. In a field of maize on a still day during high light conditions in the growing season, the CO2 concentration drops very low, but under such conditions the crop could use up to 20 times the normal concentration. The respiration of CO2 by soil microorganisms decomposing soil organic matter contributes an important amount of CO2 to the photosynthesis in plants. Within the soil, CO2 concentration is 10 to 100 times that of atmospheric but may rise to toxic levels if the soil porosity is low or if diffusion is impeded by flooding. Nitrogen. Nitrogen is the most critical element obtained by plants from the soil and is a bottleneck in plant growth. Plants can use the nitrogen as either the ammonium cation or the anion nitrate. Nitrogen is seldom missing in the soil, but is often in the form of raw organic material which cannot be used directly. The total nitrogen content depends on the climate, vegetation, topography, age and soil management. Soil nitrogen typically decreases by 0.2 to 0.3% for every temperature increase by 10 degrees Celsius. Usually, more nitrogen is under permanent grass than under forest. Humus formation promotes nitrogen immobilization. Cultivation decreases soil nitrogen, and no tillage maintains more nitrogen than tillage. Some microorganisms are able to metabolize organic matter and release ammonium in a process called mineralization. Others take free ammonium and oxidize it to nitrate. Particular bacteria are capable of metabolizing N2 into the form of nitrate in a process called nitrogen fixation. Both ammonium and nitrate can be immobilized or essentially lost from the soil by its incorporation into the microbe's living cells, where it is temporarily sequestered. Nitrate may also be lost from the soil when bacteria metabolize it to the gases N2 and N2O. The loss of gaseous forms of nitrogen to the atmosphere due to microbial action is called denitrification. Nitrogen may also be leached from the soil if it is in the form of nitrate or lost to the atmosphere as ammonia due to a chemical reaction of ammonium with alkaline soil by way of a process called volatilization. Ammonium may also be sequestered in clay by fixation. A small amount of nitrogen is added to soil by rainfall. Nitrogen gains. In the process of mineralization, microbes feed on organic matter, releasing ammonia and other nutrients. As long as the carbon-to-nitrogen ratio in the soil is above 31, nitrogen will be in short supply and other bacteria will feed on the ammonium and incorporate its nitrogen into their cells in the immobilization process. In that form the nitrogen is said to be immobilized. Later, when such bacteria die, they too are mineralized and some of the nitrogen is released as ammonium and nitrate. If the CN is less than 15, ammonia is freed to the soil, where it may be used by bacteria which oxidize it to nitrate. bacteria may on average add 25 pounds nitrogen per acre, and in an unfertilized field, this is the most important source of usable nitrogen. In a soil with 5% organic matter, perhaps 2 to 5% of that is released to the soil by such decomposition. It occurs fastest in warm, moist, well-aerated soil. The mineralization of 3% of the organic material of a soil that is 4% organic matter overall, would release 120 pounds of nitrogen as ammonium per acre. In nitrogen fixation, rhizobium bacteria convert N2 to nitrate. Rhizobia share a symbiotic relationship with host plants, since rhizobia supply the host with nitrogen and the host provides rhizobia with nutrients and a safe environment. It is estimated that such symbiotic bacteria in the root nodules of legumes add 45 to 250 pounds of nitrogen per acre per year, which may be sufficient for the crop. Other, free-living nitrogen-fixing bacteria and blue-green algae live independently in the soil and release nitrate when their dead bodies are converted by way of mineralization. Some amount of usable nitrogen is fixed by lightning as nitric oxide and nitrogen dioxide. Nitrogen dioxide is soluble in water to form nitric acid solution of H+ and NO3. Ammonia, NH3, previously released from the soil or from combustion, may fall with precipitation as nitric acid at a rate of about 5 pounds nitrogen per acre per year. Nitrogen sequestration, when bacteria feed on soluble forms of nitrogen, they temporarily sequester that nitrogen in their bodies in a process called immobilization. At a later time when those bacteria die, their nitrogen may be released as ammonium by the processes of mineralization. Protein material is easily broken down, but the rate of its decomposition is slowed by its attachment to the crystalline structure of clay and trapped between the clay layers. The layers are small enough that bacteria cannot enter. Some organisms can exude extracellular enzymes that can act on the sequestered proteins. However, those enzymes too may be trapped on the clay crystals. Ammonium fixation occurs when ammonium replaces the potassium ions that normally exist between the layers of clay such as alite or montmorillonite. Only a small fraction of nitrogen is held this way. Nitrogen losses. Usable nitrogen may be lost from soils when it is in the form of nitrate, as it is easily leached. Further losses of nitrogen occur by denitrification, the process whereby soil bacteria convert nitrate to nitrogen gas, N2 or N2O. This occurs when poor soil aeration limits free oxygen, forcing bacteria to use the oxygen in nitrate for their respiratory process. Denitrification increases when oxidizable organic material is available and when soils are warm and slightly acidic. Denitrification may vary throughout a soil as the aeration varies from place to place. Denitrification may cause the loss of 10 to 20% of the available nitrates within a day, and when conditions are favorable to that process, losses of up to 60% of nitrate applied as fertilizer may occur. Ammonium volatilization occurs when ammonium reacts chemically with an alkaline soil, converting NH4+ to NH3. The application of ammonium fertilizer to such a field can result in volatilization losses of as much as 30%. Phosphorus. Phosphorus is the second most critical plant nutrient. The soil mineral apatite is the most common mineral source of phosphorus. While there is on average 1,000 lb of phosphorus per acre in the soil, it is generally unavailable in the form of phosphates of low solubility. Total phosphorus is about 0.1% by weight of the soil, but only 1% of that is available. Of the part available, more than half comes from the mineralization of organic matter. Agricultural fields may need to be fertilized to make up for the phosphorus that has been removed in the crop. When phosphorus does form solubilized ions of H2PO4, they rapidly form insoluble phosphates of calcium or hydrous oxides of iron and aluminum. Phosphorus is largely immobile in the soil and is not leached but actually builds up in the surface layer if not cropped. The application of soluble fertilizers to soils may result in zinc deficiencies as zinc phosphates form. Conversely, the application of zinc to soils may immobilize phosphorus again as zinc phosphate. Lack of phosphorus may interfere with the normal opening of the plant leaf stomata, resulting in plant temperatures 10% higher than normal. Phosphorus is most available when soil pH is 6.5 in mineral soils and 5.5 in organic soils. Potassium, the amount of potassium in a soil may be as much as 80,000 lb per acre, of which only 150 lb or 2% is available for plant growth. Common mineral sources of potassium are the microbiotite and potassium feldspar, Cal C308. When solubilized, half will be held as exchangeable cations on clay while the other half is in the soil water solution. Potassium fixation occurs when soils dry and the potassium is bonded between layers of clay. Under certain conditions, dependent on the soil texture, intensity of drying, and initial amount of exchangeable potassium, the fixed percentage may be as much as 90% within 10 minutes. Potassium may be leached from soils low in clay. Calcium is 1% by weight of soils and is generally available but may be low as it is soluble and can be leached. It is thus low in sandy and heavily leached soil or strongly acidic mineral soil. Calcium is supplied to the plant in the form of exchangeable ions and moderately soluble minerals. Calcium is more available on the soil colloids than is potassium because the common mineral calcite, CaCO3, is more soluble than potassium-bearing minerals. Magnesium is central to chlorophyll and aids in the uptake of phosphorus. The minimum amount of magnesium required for plant health is not sufficient for the health of forage animals. A common mineral source of magnesium is the black micromineral, biotite. Magnesium is generally available in soil, but is missing from some along the Gulf and Atlantic coasts of the United States due to leaching by heavy precipitation. Sulfur. Most sulfur is made available to plants, like phosphorus, by its release from decomposing organic matter. Deficiencies may exist in some soils and if cropped, sulfur needs to be added. A 15-ton crop of onions uses up to 19 lb of sulfur and 4 tons of alfalfa uses 15 lb per acre. Sulfur abundance varies with depth. In a sample of soils in Ohio, United States, the sulfur abundance varied with depths, 0-6 inches, 6-12 inches, 12-18 inches, 18-24 inches in the amounts, 1056, 830, 686, 528 lb per acre respectively. Micronutrients. The micronutrients essential for plant life, in their order of importance, include iron, manganese, zinc, copper, boron, chlorine and molybdenum. The term refers to plants' needs, not to their abundance in soil. They are required in very small amounts but are essential to plant health in that most are required parts of some enzyme system which speeds up plants' metabolisms. They are generally available in the mineral component of the soil, but the heavy application of phosphates can cause a deficiency in zinc and iron by the formation of insoluble zinc and iron phosphates. Iron deficiency may also result from excessive amounts of heavy metals or calcium minerals in the soil. Excess amounts of soluble boron, molybdenum and chloride are toxic. Non-essential nutrients, nutrients which enhance the health but whose deficiency does not stop the life cycle of plants include cobalt, strontium, vanadium, silicon and nickel. As their importance are evaluated they may be added to the list of essential plant nutrients. Organic matter. Organic soil matter are compounds of carbon that includes all plant and animal material both alive or dead. A typical soil has a biomass composition of 70% microorganisms, 22% macrofauna, and 8% roots. The living component of an acre of soil may include 900 lb of earthworms, 2400 lb of fungi, 1500 lb of bacteria, 133 lb of protozoa and 890 lb of arthropods and algae. A small part of the organic matter is made of the living cells such as bacteria, molds, and actinomycetes that work to break down the organic matter. Were it not for the action of these microorganisms, the entire carbon dioxide part of the atmosphere would be sequestered as organic matter in the soil. Chemically, organic matter is classed as follows: 1. Polysaccharides, A. Cellulose, B. Hemicellulose, C. Starch, D. Pectine. 2. Lignins, 3. Proteins. Most living things in soils, including plants, insects, bacteria, and fungi, are dependent on organic matter for nutrients and energy. Soils have organic compounds in varying degrees of decomposition, which rate is dependent on the temperature, soil moisture, and aeration. Bacteria and fungi feed on the raw organic matter, which are fed upon by amoebas, which in turn are fed upon by nematodes and arthropods. Organic matter holds soils open, allowing the infiltration of air and water, and may hold as much as twice its weight in water. Many soils, including desert and rocky gravel soils, have little or no organic matter. Soils that are all organic matter, such as peat, are infertile. In its earliest stage of decomposition, the original organic material is often called raw organic matter. The final stage of decomposition is called humus. In grassland, much of the organic matter added to the soil is from the deep, fibrous, grass root systems. By contrast, tree leaves falling on the forest floor are the principal source of soil organic matter in the forest. Another difference is the frequent occurrence in the grasslands of fires that destroy large amounts of above-ground material but stimulate even greater contributions from roots. Also, the much greater acidity under any forests inhibits the action of certain soil organisms that otherwise would mix much of the surface litter into the mineral soil. As a result, the soils under grasslands generally develop a thicker A horizon with a deeper distribution of organic matter than incomparable soils under forests, which characteristically store most of their organic matter in the forest floor and thin A horizon. Humus. Humus refers to organic matter that has been decomposed by soil flora and fauna to the point where it is resistant to further breakdown. Humus usually constitutes only 5% of the soil or less by volume, but it is an essential source of nutrients and adds important textural qualities crucial to soil health and plant growth. Humus also holds bits of undecomposed organic matter which feed arthropods and worms, which further improve the soil. The end product, humus, is soluble in water and forms a weak acid that can attack silicate minerals. Humus has a high cation exchange capacity that on a dry weight basis is many times greater than that of clay colloids. It also acts as a buffer, like clay, against changes in pH and soil moisture. Humic acids and fulvic acids, which begin as raw organic matter, are important constituents of humus. After the death of plants and animals, microbes begin to feed on the residues, resulting finally in the formation of humus. With decomposition, there is a reduction of water-soluble constituents, cellulose and hemicellulose, and nutrients such as nitrogen, phosphorus, and sulfur. As the residues break down, only stable molecules made of aromatic carbon rings, oxygen and hydrogen remain in the form of humin, lignin and lignin complexes as humus. While the structure of humus has few nutrients, it is able to attract and hold cation and anion nutrients by weak bonds that can be released in response to changes in soil pH. Lignin is resistant to breakdown and accumulates within the soil. It also reacts with amino acids, which further increases its resistance to decomposition, including enzymatic decomposition by microbes. Fats and waxes from plant matter have some resistance to decomposition and persist in soils for a while. Clay soils often have higher organic contents that persist longer than soils without clay, as the organic molecules adhere to and are stabilized by the clay. Proteins normally decompose readily, but when bound to clay particles, they become more resistant to decomposition. Clay particles also absorb the enzymes exuded by microbes which would normally break down proteins. The addition of organic matter to clay soils can render that organic matter and any added nutrients inaccessible to plants and microbes for many years. High soil tannin content can cause nitrogen to be sequestered in proteins or cause nitrogen immobilization. Humus formation is a process dependent on the amount of plant material added each year and the type of base soil. Both are affected by climate and the type of organisms present. Soils with humus can vary in nitrogen content but typically have 3 to 6% nitrogen. Raw organic matter, as a reserve of nitrogen and phosphorus, is a vital component affecting soil fertility. Humus also absorbs water, and expands and shrinks between dry and wet states, increasing soil porosity. Humus is less stable than the soil's mineral constituents, as it is reduced by microbial decomposition, and over time its concentration diminishes without the addition of new organic matter. However, humus may persist over centuries if not millennia. Climate and organics, the production, accumulation and degradation of organic matter are greatly dependent on climate. Temperature, soil moisture and topography are the major factors affecting the accumulation of organic matter in soils. Organic matter tends to accumulate under wet or cold conditions where decomposer activity is impeded by low temperature or excess moisture, which results in anaerobic conditions. Conversely, excessive rain and high temperatures of tropical climates will allow microbes to destroy organic matter and the nutrients to be leached from the soil to the point that the humus and nutrients essentially does not exist. Excessive slope may encourage the erosion of the top layer of soil, which holds most of the raw organic material that would otherwise eventually become humus. Plant residue in soil. Cellulose is the most abundant of plant residue. Cellulose is composed of up to 14,000 glucose units. Cellulose undergoes slow decomposition by fungi and bacteria. Hemicellulose is the second most abundant of plant residue. Hemicellulose consists of polymers of sugars composed of 50 to 200 units with an amorphous structure of little strength. Hemicellulose undergoes fast decomposition by fungi and bacteria. Brown rot fungi can decompose the cellulose and hemicellulose, leaving the lignin and phenolic compounds behind. Starch, which is an energy storage system for plants, undergoes fast decomposition by bacteria and fungi. Lignin consists of polymers composed of 500 to 600 units with a highly branched, amorphous structure. Lignin undergoes very slow decomposition, only by white rot fungi and actinomycetes. Soil horizons. A horizontal layer of the soil, whose physical features, composition and age are distinct from those above and beneath, are referred to as a soil horizon. The naming of a horizon is based on the type of material of which it is composed. Those materials reflect the duration of specific processes of soil formation. They are labeled using a shorthand notation of letters and numbers which describe the horizon in terms of its color, size, texture, structure, consistency, root quantity, pH, voids, boundary characteristics and presence of nodules or concretions. Few soil profiles have all the major horizons. Some may have only one horizon. The exposure of parent material to favorable conditions produces mineral soils that are marginally suitable for plant growth. That growth often results in the accumulation of organic residues. The accumulated organic layer called the O horizon produces a more active soil due to the effect of the organisms that live within it. Organisms colonize and break down organic materials, making available nutrients upon which other plants and animals can live. After sufficient time, humus moves downward and is deposited in a distinctive organic surface layer called the A horizon. Classification. Soil is classified into categories in order to understand relationships between different soils and to determine the suitability of a soil for a particular use. One of the first classification systems was developed by the Russian scientist Decomposition around 1880. It was modified a number of times by American and European researchers, and developed into the system commonly used until the 1960s. It was based on the idea that soils have a particular morphology based on the materials and factors that form them. In the 1960s, a different classification system began to emerge which focused on soil morphology instead of parental materials and soil-forming factors. Since then it has undergone further modifications. The World Reference Base for Soil Resources aims to establish an international reference base for soil classification. Soil taxonomy. A taxonomy is an arrangement in a systematic manner. Soil taxonomy has 6 categories. They are, from most general to specific, order, suborder, grade group, subgroup, family and series. The soil properties that can be measured quantitatively are used to classify soils. A partial list is depth, moisture, temperature, texture, structure, cation exchange capacity, base saturation, clay mineralogy, organic matter content and salt content. Australia. There are 14 soil orders at the top level of the Australian soil classification. They are anthroposols, organosols, podosols, vertisols, hydrosols, corosols, sodosols, chromosols, calcarosols, ferrosols, dermasols, candisols, rudosols and tenosols. European Union. The EU's soil taxonomy is based on a new standard soil classification in the World Reference Base for Soil Resources produced by the UN's Food and Agriculture Organization. According to this, the major soils in the European Union are acrisols, albulifosols, andisols, anthrosols, arnosols, calcisols, cambisols, cheronisms, flavosols, glycols, gypsosols, histosols, castanisms, leptosols, levosols, piezosols, planosols, podsols, regosols, salonchaks, salonetses, umbrisols, vertisols, USA. In the United States, soil orders are the top hierarchical level of soil classification in the USDA soil taxonomy. The names of the orders end with the suffix -sol. There are 12 soil orders in soil taxonomy. The criteria for the order divisions include properties that reflect major differences in the genesis of soils. Artificial, soils with aluminium and iron. They have horizons of clay accumulation, and form where there is enough moisture and warmth for at least 3 months of plant growth. They constitute 10.1% of soils worldwide. Andisols, volcanic ash soils. They are young and very fertile. They cover 1% of the world's ice-free surface. Aridisol, dry soils forming under desert conditions which have fewer than 90 consecutive days of moisture during the growing season and are non-leached. They include nearly 12% of soils on Earth. Soil formation is slow, and accumulated organic matter is scarce. They may have subsurface zones of caliche or diripan. Many aridisols have well-developed BT horizons showing clay movement from past periods of greater moisture. Entisol, recently formed soils that lack well-developed horizons. Commonly found on unconsolidated river and beach sediments of sand and clay or volcanic ash, some have an A horizon on top of bedrock. There are 18% of soils worldwide. Gelisols, permafrost soils with permafrost within 2 meters of the surface or gelic materials and permafrost within 1 meter. They constitute 9.1% of soils worldwide. Histosol, organic soils, formerly called bog soils, are 1.2% of soils worldwide. Inceptisol, young soils. They have subsurface horizon formation but show little alluviation and alluviation. They constitute 15% of soils worldwide. Mollisols, soft, deep, dark fertile soil formed in grasslands and some hardwood forests with very thick A horizons. They are 7% of soils worldwide. Oaksol, are heavily weathered, are rich in iron and aluminum oxides or kaolin but low in silica. They have only trace nutrients due to heavy tropical rainfall and high temperatures. They are 7.5% of soils worldwide. Spodosol, acid soils with organic colloid layer complexed with iron and aluminium leached from a layer above. They are typical soils of coniferous and deciduous forests in cooler climates. They constitute 4% of soils worldwide. Altisol, acid soils in humid climates, tropical to subtropical temperatures, which are heavily leached of Ca, Mg, and K nutrients. They are not quite oxysols. They are 8.1% of the soil worldwide. Vertisol, inverted soils. They are clay-rich and tend to swell when wet and shrink upon drying, often forming deep cracks into which surface layers can fall. They are difficult to farm or to construct roads and buildings due to their high expansion rate. They constitute 2.4% of soils worldwide. The percentages listed above are for land area free of ice. Soils of mountains, which constitute the balance, have a mixture of those listed above, or are classified as rugged mountains, which have no soil. The above soil orders in sequence of increasing degree of development are entisols, inceptisols, aridisols, mollisols, alfisols, spodosols, altisols, and oxysols. Histosols and vertisols may appear in any of the above at any time during their development. The soil suborders within an order are differentiated on the basis of soil properties and horizons which depend on soil moisture and temperature. 47 suborders are recognized in the United States. The soil grade group category is a subdivision of a suborder in which the kind and sequence of soil horizons distinguish one soil from another. About 185 grade groups are recognized in the United States. Horizons marked by clay, iron, humus and hard pans and soil features such as the expansion-contraction of clays, temperature, and marked quantities of various salts are used as distinguishing features. The grade group categories are divided into three kinds of soil subgroups: typic, intergrade and extragrade. A typic subgroup represents the basic or typical concept of the grade group to which the described subgroup belongs. An intergrade subgroup describes the properties that suggest how it grades towards soils of other soil grade groups, suborders or orders. These properties are not developed or expressed well enough to cause the soil to be included within the grade group towards which they grade, but suggest similarities. Extragrade features are aberrant properties which prevent that soil from being included in another soil classification. About 1,000 soil subgroups are defined in the United States. A soil family category is a group of soils within a subgroup and describes the physical and chemical properties which affect the response of soil to agricultural management and engineering applications. The principal characteristics used to differentiate soil families include texture, mineralogy, pH, permeability, structure, consistency, the locale's precipitation pattern, and soil temperature. For some soils the criteria also specify the percentage of silt, sand and coarse fragments such as gravel, cobbles and rocks. About 4,500 soil families are recognized in the United States. A family may contain several soil series which describe the physical location using the name of a prominent physical feature such as a river or town near where the soil sample was taken. An example would be Merrimack for the Merrimack River in New Hampshire, USA. More than 14,000 soil series are recognized in the United States. This permits very specific descriptions of soils. A soil phase of series, originally called soil type, describes the soil surface texture, slope, stoniness, saltiness, erosion, and other conditions. Uses: soil is used in agriculture, where it serves as the anchor and primary nutrient base for plants. However, as demonstrated by hydroponics, it is not essential to plant growth if the soil-contained nutrients can be dissolved in a solution. The types of soil and available moisture determine the species of plants that can be cultivated. Soil material is also a critical component in the mining, construction and landscape development industries. Soil serves as a foundation for most construction projects. The movement of massive volumes of soil can be involved in surface mining, road building and dam construction. Earth sheltering is the architectural practice of using soil for external thermal mass against building walls. Soil resources are critical to the environment, as well as to food and fiber production. Soil provides minerals and water to plants. Soil absorbs rainwater and releases it later, thus preventing floods and drought. Soil cleans water as it percolates through it. Soil is the habitat for many organisms. The major part of known and unknown biodiversity is in the soil, in the form of invertebrates, bacteria, archaea, fungi and algae. And most organisms living above ground have part of them or spend part of their life cycle below ground. Above ground and below ground biodiversities are tightly interconnected, making soil protection of paramount importance for any restoration or conservation plan. The biological component of soil is an extremely important carbon sink since about 57% of the biotic content is carbon. Even on desert crusts, cyanobacteria, lichens and mosses capture and sequester a significant amount of carbon by photosynthesis. Poor farming and grazing methods have degraded soils and released much of this sequestered carbon to the atmosphere. Restoring the world's soils could offset some of the huge increase in greenhouse gases causing global warming, while improving crop yields and reducing water needs. Waste management often has a soil component. Septic drain fields treat septic tank effluent using aerobic soil processes. Landfills use soil for daily cover. Land application of wastewater relies on soil biology to aerobically treat BOD. Organic soils, especially peat, serve as a significant fuel resource. But wide areas of peat production, such as sphagnum bogs, are now protected because of patrimonial interest. Geophagy is the practice of eating soil-like substances. Both animals and human cultures occasionally consume soil for medicinal, recreational, or religious purposes. It has been shown that some monkeys consume soil, together with their preferred food, in order to alleviate tannin toxicity. Soils filter and purify water and affect its chemistry. Rainwater and pooled water from ponds, lakes and rivers percolate through the soil horizons and the upper rock strata, thus becoming groundwater. Pests and pollutants, such as persistent organic pollutants, oils, heavy metals, and excess nutrients are filtered out by the soil. Soil organisms metabolize them or immobilize them in their biomass and necromass, thereby incorporating them into stable humus. The physical integrity of soil is also a prerequisite for avoiding landslides and rugged landscapes. Degradation. Land degradation refers to a human-induced or natural process which impairs the capacity of land to function. Soils are the critical component in land degradation when it involves acidification, contamination, desertification, erosion or salination. While soil acidification is beneficial in the case of alkaline soils, it degrades land when it lowers crop productivity and increases soil vulnerability to contamination and erosion. Soils are often initially acid because their parent materials were acid and initially low in the basic cations. Acidification occurs when these elements are leached from the soil profile by rainfall or by harvesting of forest or agricultural crops. Soil acidification is accelerated by the use of acid-forming nitrogenous fertilizers and by the effects of acid precipitation. Soil contamination at low levels is often within soil's capacity to treat and assimilate waste material. Soil biota can treat waste by transforming it. Soil colloids can absorb waste material. Many waste treatment processes rely on this treatment capacity. Exceeding treatment capacity can damage soil biota and limit soil function. Derelict soils occur where industrial contamination or other development activity damages the soil to such a degree that the land cannot be used safely or productively. Remediation of derelict soil uses principles of geology, physics, chemistry and biology to degrade, attenuate, isolate or remove soil contaminants to restore soil functions and values. Techniques include leaching, air sparging, chemical amendments, phytoremediation, biomediation and natural degradation. Desertification is an environmental process of ecosystem degradation in arid and semi-arid regions, often caused by human activity. It is a common misconception that droughts cause desertification. Droughts are common in arid and semi-arid lands. Well-managed lands can recover from drought when the rains return. Soil management tools include maintaining soil nutrient and organic matter levels, reduced tillage and increased cover. These practices help to control erosion and maintain productivity during periods when moisture is available. Continued land abuse during droughts, however, increases land degradation. Increased population and livestock pressure on marginal lands accelerates desertification. Erosion of soil is caused by water, wind, ice, and movement in response to gravity. More than one kind of erosion can occur simultaneously. Erosion is distinguished from weathering, since erosion also transports eroded soil away from its place of origin. Erosion is an intrinsic natural process, but in many places it is greatly increased by human activity, especially poor land use practices. These include agricultural activities which leave the soil bare during times of heavy rain or strong winds, overgrazing, deforestation, and improper construction activity. Improved management can limit erosion. Soil conservation techniques which are employed include changes of land use, changes to the timing or type of agricultural operations, terrace building, use of erosion-suppressing cover materials, limiting disturbance during construction, and avoiding construction during erosion-prone periods. A serious and long-running water erosion problem occurs in China, on the middle reaches of the Yellow River and the upper reaches of the Yangtze River. From the Yellow River, over 1.6 billion tons of sediment flow each year into the ocean. The sediment originates primarily from water erosion in the Loess Plateau region of northwest China. Soil piping is a particular form of soil erosion that occurs below the soil surface. It causes levee and dam failure, as well as sinkhole formation. Turbulent flow removes soil starting at the mouth of the seep flow and the subsoil erosion advances up gradient. The term sand boil is used to describe the appearance of the discharging end of an active soil pipe. Soil salination is the accumulation of free salts to such an extent that it leads to degradation of the agricultural value of soils and vegetation. Consequences include corrosion damage, reduced plant growth, erosion due to loss of plant cover and soil structure, and water quality problems due to sedimentation. Salination occurs due to a combination of natural and human-caused processes. Arid conditions favor salt accumulation. This is especially apparent when soil parent material is saline. Irrigation of arid lands is especially problematic. All irrigation water has some level of salinity. Irrigation, especially when it involves leakage from canals and over-irrigation in the field, often raises the underlying water table. Rapid salination occurs when the land surface is within the capillary fringe of saline groundwater. Soil salinity control involves water table control and flushing with higher levels of applied water in combination with tile drainage or another form of subsurface drainage. Reclamation, soils which contain high levels of particular clays, such as smectites, are often very fertile. For example, the smectite-rich clays of Thailand's central plains are among the most productive in the world. Many farmers in tropical areas, however, struggle to retain organic matter in the soils they work. In recent years, for example, productivity has declined in the low clay soils of northern Thailand. Farmers initially responded by adding organic matter from termite mounds, but this was unsustainable in the long term. Scientists experimented with adding bentonite, one of the smectite family of clays, to the soil. In field trials, conducted by scientists from the International Water Management Institute in cooperation with Konkan University and local farmers, this had the effect of helping retain water and nutrients. Supplementing the farmer's usual practice with a single application of 200 kg bentonite per re resulted in an average yield increase of 73%. More work showed that applying bentonite to degraded sandy soils reduced the risk of crop failure during drought years. In 2008, 3 years after the initial trials, IWMI scientists conducted a survey among 250 farmers in northeast Thailand, half of whom had applied bentonite to their fields. The average improvement for those using the clay addition was 18% higher than for non-clay users. Using the clay had enabled some farmers to switch to growing vegetables, which need more fertile soil. This helped to increase their income. The researchers estimated that 200 farmers in northeast Thailand and 400 in Cambodia had adopted the use of clays, and that a further 20,000 farmers were introduced to the new technique. If the soil is too high in clay, adding gypsum, washed river sand and organic matter will balance the composition. Adding organic matter to soil which is depleted in nutrients and too high in sand will boost its quality. See also, references, citations. Sources. Further reading. External links.